Okay. Yeah, so I didn't cover absolutely everything, like I was saying, Gaussian elimination. To find an inverse of a matrix is something you should study on your own. But yeah, I think we're getting a lot of things in here. Okay, let's look at a couple of things out of chapter 1. This is number 6. Just going to start with a word problem here, okay? So a tank with volume 200 liters is initially half full of a solution with 70 grams of chemical. Okay? So then a solution with 1/2 gram per liter flows into the tank at 6 liters per minute, and the mixture flows out at 4 liters per minute. Find the amount of chemical in the tank after 1 hour. Okay? So, what kind of a problem is this? Definitely a mixing problem, okay. So that's from section 1.7. So let's write down the differential equation that governs that. So apparently I put some note that I was going to give you the formula, which I didn't remember doing, but I take your report. So the formula for the differential equation for this is that the rate of change of the amount of the chemical as a function of time, whoops, it's not equal. So dA dt plus, the notation is R2 over VA equals R1 C1. So you have to remember what all these letters mean, right? Here's your tank, and everything is flowing in at a rate of R1 and a concentration of C1. And then everything flows out at a rate of R2, and the concentration coming out is C2, but that actually doesn't appear. You don't really need that, so just leave it like that. Really, the C2 is just A over V, because that's the concentration in the tank, and that's what leaves the tank. So this is your differential equation. And so can somebody tell me any of the numbers that we know so far?
Initial volume.
Okay, the initial volume, that would be V of 0, would be what? Say again?
200.
Right, so 100. That's because it's half full, right? So 200 liters, but it's half full. You just have to read the question very carefully. Okay, so that's 100. Okay, what other numbers do we know?
C1 equals 1/2.
Okay, C1, which is the concentration going in, is 1/2. Chelsea, you wanted to tell me something? No. Okay, I thought you were. Well, since I called on you, can you tell me one of the other numbers? Yeah, the rate of flow into the tank is 6. Okay. Mercy, do you want to give me one of the other numbers?
R2 is 4.
Good. R2 is 4. Okay, and does anybody know the formula for the V on the bottom, the volume?
Plus R1 minus R2 times T.
Right. R1 minus R2 times T is the right formula. So, oh, and that's
Plus
plus the initial, right?
Yeah.
So plus the V0 or V of 0 here. Okay, so that's a good one to know. Basically, whatever the initial volume is might be changing with time if the rates in and out are different. So what does this equal for our problem? 6 minus 4 is 2, so we have 2t plus V of 0, which we said was 100, right? Yeah.
Don't you also have your initial amount of 70 grams?
Ah, okay, the initial amount, so that would be A of 0, I'll put that over here. A of 0 was 70 grams. Does that go in the equation anywhere? Right, this is actually called the initial condition. So what we have in these mixing problems is not just a differential equation. We have a differential equation together with an initial condition, and that gives you what's called an initial value problem. The way we tackle this is we're going to solve for the general solution to the differential equation. You guys have seen examples of this too. We find the general solution, which has a constant in it, and then you use the initial condition later to find the constant and get the particular solution that you're looking for. So a differential equation, the solution to a differential equation is not just one function, it's a whole family of functions, right? Just like if you drop some object through space, right? Basically the solution is going to be a parabola, 1/2 gt squared plus ct plus d. But then the c and the d could change, right? It's just a whole bunch of different parabolas, and which one's the one that you need to work with depends on the initial conditions. That reminds me, you maybe make a note to yourself, those distance, velocity, acceleration problems we did the very first week of the semester. It's a good application of differential equations. It's an easy one because you just have to integrate twice, but then using the initial conditions is maybe the harder part of that. Anyway, getting back to this, basically we're going to find the general solution first and then solve for the initial condition. Yeah.
Based on this right here, you can't get overflow.
Probably. Hopefully it doesn't overflow within the first hour.
No, it will.
It will.
They alternate to 220.
Oh no. What are we going to do about that?
7 minutes.
Yeah, I could say find the amount of chemical in the tank after half of an hour. That might be better. Oh shoot, I didn't even realize that. Yeah, because 1 hour, and that's a good point. Everything else is in minutes except for this. That was kind of on purpose. You have to remember that you really have to convert this to minutes. So 1 hour is really 60 minutes. If I put in 60 for T, I get 220. And my tank isn't big enough.
You just do a 400-liter tank to make it quarter full.
Hey, there you go. A tank with a volume of 400 liters. I like the way you think. Is initially 1/4 full. We saved the day.
Can we do that in the test?
Yeah, just change the problem. Anytime you don't like the question, just go ahead and change it to what you want.
Well, if we end up
Okay.
finding this, could we just say, can't make it to the 1 hour solution?
Probably if you get stuck on something like this, you probably ought to come talk to me up in the front of the room and see if I have a heart attack because my question didn't work out. I do, when I write my tests, I always write the solutions to it before the test as well, just to make sure everything works. And I didn't check this one lately, so I didn't think that there was a problem with it. Anyway, you made a good point, very good point. Okay, getting back to this, let's start plugging in the numbers here. So we have dA dt. R2 was 4, and I have to divide that by the volume, which is 2T plus 100 times A. And then R1 times C1 is 3, right? Okay. It would probably be a good idea to simplify that slightly because there's factors of 2 everywhere here. So let's divide through by 2. We have 2 over T plus 50 times A equals 3. That's our equation. And this is always going to be first order linear. So it's already in the right form for first order linear. This is this part right here, this whole thing would be what we call the P of T, and this is the Q of T right here. Okay, so what do we need to do to solve this? Right, the integrating factor, exactly, good. Okay, so let's find the integrating factor. This is one of the formulas on the list that we put together earlier. So it's e to the integral of the P of T, which is 2 over T plus 50 dt, right? And this is pretty easy to solve it. Just this integration is not too bad because, well, you can pull out the 2 if you want. The 2 is just a constant. Pull it out, and then you're integrating 1 over t plus 50. What is the integral of 1 over t plus 50? Say again? Good. ln of t plus 50, and I'm not going to bother with absolute value bars here because t is going to be a positive time anyway. So this is a positive amount. And normally I have to put plus c on the end of this. Do I do that here? Not necessary, right? It wouldn't be wrong to do it, but you could choose the c to be 0 so that you don't have to worry about it. Okay, can this be simplified? Okay, good. I hope everybody has done enough of these that you do them kind of quickly because, and carefully of course, because you do need to be able to do this. Basically the 2 comes upstairs as a power so that the e and the ln can cancel. So you're just going to get t plus 50 squared. Okay? And then from there, once you have the integrating factor, then the next piece of this is that if you take the integrating factor times the unknown function, which in this case is a, and you take the quantity derivative of that, you're supposed to get the right-hand side, which is 3 times the integrating factor, which is t plus 50 squared. Okay? So that is the new problem that you come up with. And you may want to just memorize that also, that that's what it becomes. So the integrating factor times the unknown function in a product rule derivative, right, equaling, the right-hand side is just the q times the integrating factor. And what do I need to do next? Exactly. I have to integrate both sides because on the left, if I integrate both sides, on the left I just get back to my original, the integral undoes the derivative and leaves you with the inside piece. What do I get when I integrate 3 times t plus 50 quantity squared? Exactly. T plus 50 quantity cubed. You can just double check the derivative of this is 3 times t plus 50 squared times 1. Now if there was a number in front of this t, you have to be a little more careful. You probably want to do it as a u substitution. But here you can kind of see it in your head that this is what it becomes. Do I need anything else here? Exactly. This time I do need the plus c. I do need the plus c. Okay, so let's divide through by t plus 50 squared. So we have t plus 50 cubed plus c all over t plus 50 squared. Okay. All right. So this is the general solution, which is an infinite family of solutions that we can use. So what do I need to do next? Exactly, a of 0, right? We want to do that so we can figure out what c is. So if I put in 0, a of 0 is going to be 50 cubed plus c all over 50 squared, and it's supposed to equal 70. Okay. Does anybody have a calculator?
You can't use those on the
You can't on the test, but we can use it now. If somebody has a calculator, I'd like to know what is 70 times 50 squared minus 50 cubed. I want to solve for c, basically.
50,000.
Is it 50,000? Okay, I'll take your word for that. So c is 50,000. Actually, hold on, I have the solution, so I can just check it. That sounds right. That's probably right. I just don't want to have it wrong, for sure. Yeah, 50,000, good. That's exactly what I have. All right, good. So then, so once we know that it's 50,000, then we have our a of t formula, which is going to be t plus 50 cubed plus 50,000, all divided by t plus 50 squared. That is the final formula for a of t. And now, we just have the last step, which is to plug in 60 minutes. Right, so A of 60, I put in 60 for T, right? I'm gonna get 110 cubed plus 50,000 divided by 110 squared. You know, that would be, on a test, a fine answer. I don't mind you leaving it like that. You don't have to simplify it. But in my solutions to these problems, by the way, all these problems are solved on the internet already. If you look at my solutions to them, you'll find an exact value.
So that would be the final answer.
Yes. Final answer right here. A of 60 is 110 cubed plus 50,000, all divided by 110 squared. Okay? So this is practicing one of the applications. Of course, there's also, there's Newton's law of cooling. I'm not going to do one of those tonight, I don't think. And then there's the gravitational, distance velocity acceleration application. Yes?
Would you give like both of them, or would you give?
Probably not both. It's maybe too much. I'm not sure. I could ask like one conceptual question maybe or something, and then one calculation question. But yeah, I tend to like to spread the test out. Like it's going to be covering everything, so I don't want to like have all these questions about every single thing from one chapter, and then run out of space on the exam to put things from other chapters. So, but I'm not sure. I haven't read the test yet. So think about it. Don't hold me to them. Okay. Anything else before we go on? I'm going to just do one more problem and then we'll call it a night. Probably do one more problem before I collapse. Kind of a long day. I was reading scholarship applications and it was really boring. I had to read them. Many of these things are very, very hard to read, so it kind of takes it out of it. Okay, number 7. Solve 2xy prime equals 4x squared plus 3y squared. Get down to the nuts and bolts. You remember how I did the quiz? I think I gave you like 3 differential equations. I asked you to classify them, and then I asked you to solve like one of them. Not a bad thing to be prepared to do, right? If I ask that again, back on a test, I might ask you to prove more than one of them. You have to solve more than one of them. But you need to be able to classify these things, so you can practice that. There's a lot of good examples to practice on. But we've sort of studied 4 different types of equations, right? Separable, linear, Bernoulli, and homogeneous. So those are kind of the ones you want to be looking out for. If it was going to be anything other than those 4, right, I would pretty much have to tell you sort of how to approach it, because it would be like something you hadn't seen before. But if it's one of those 4 types, we should be able to do it. So what do you think? Oh, wow, you guys are fast. So how do you decide if something's homogeneous?
Put T next to all the variables and put the formula on.
Usually I like to have it solve for y prime first, and then I go through that process, because whether the t's factor, the t has nothing to do with the y prime, it's just the x and y. So if you rewrite the equation in this manner, if you stick a t next to every single x, including if it occurs multiple times, and every single y, you look to see if it cancels itself back out. And in this case, it does, right? So if I put a t next to that x, next to that y, so I'll have 2 t's on top. And then there's a t next to this x and a t next to this y. That's 2 t's on the bottom, so they cancel out. Yes?
So for the x squared, you would have x squared t squared.
Well, you have xt quantity squared, which is the same as x squared t squared.
Oh, okay.
Yeah, you can just do this. Just go ahead and write the whole thing out. Easier for you to see it. Right, so if you write it like that, now you see that there's 2 t's here, there's 2 t's here, and there's 2 t's here. So this does simplify back down to the original thing on the right-hand side. Yeah, so this is homogeneous. So if this equation is homogeneous, you remember how to approach it? Say again?
Change the y.
And how do you do that? Yeah, x times v or v times x, right? And then the derivative of that, we just use the product rule. So it's x times the derivative of v plus v times the derivative of x, which is 1, because you're differentiating with respect to x. Okay? So these are going to be your substitutions that you need, right? So on the left side, of course, you're just going to, so I'm going to take this thing now and substitute. On the left side, I'm just going to get xv prime plus v. And then on the right-hand side, basically I want to get rid of all the y's. So to get rid of all the y's, I'm going to have 2x times y, which is xv. And on top, I'm going to have 4x squared plus 3 times, let's see, y squared would be xv squared. So it looks like that. Yeah,
You
Rosalie?
just replace the y with x, right?
Yeah. That's all that I did. So now there's no more y's, there's only x's and v's. Does this simplify at all?
Yeah.
How can I simplify it?
You could pull out an x squared cancel them out and the numerator combined.
Yeah, the x squareds on top and bottom are completely factorable and cancelable. So if I do that, I'll have 4 plus 3v squared all over 2v, right? And keep in mind that still equals xv prime plus v. Okay? Let me actually come back over here and use this side. What can I do with that? Did we simplify? It's supposed to always become what again? Separable. So I should be able to get all the v's on one side and all of the x's on the other side. So how might I try to get that to happen?
When you change the v prime.
Yeah, I can change the v prime. Good. So let's do that. So we're going to have x and then dv over dx. And I can already see all of the v stuff on the right side. So why don't I subtract this v over, right? So let's just do that. So we'll leave this like this, equals 4 plus 3v squared all over 2v, and then just subtract v from it. So let's kind of get all the v stuff together. Okay. Any suggestions from there?
3 half v
So you're getting 3 halves v, here's 3 halves, and v squared over v is v, right?
Yeah.
So to do that, you have to actually
Yeah.
split the fraction. And guys, be careful, when you have, like, this is just algebra then. If you have a fraction like that, it's perfectly good to split it apart, right? But what you don't want to do is try and play that game with the denominator. This cannot be pulled apart. Okay, but here I can. So 4 over 2v is 2 over v. 3 halves v minus v is 1 half v. Excuse me. Okay. What now?
Can you change the plus 1 half v to negative 1 half v with that minus v at the top?
Well, so here what I did, I already subtracted this v into this part. So we had 3 halves of v, and I subtracted v, and I got just 1 half v. Yeah. How about we just try to do a common denominator on a fraction? Just make a common denominator here. That seems like a reasonable algebra step. If I do that, then the 2 becomes a 4. So 4 over 2v is really just the same as 2 over v, right? And then plus, And then here, we put a v on the bottom, so I also have to put it on top. So it'll look like that. Okay, so just make a common denominator. We could have even done that up here originally. And the first step is go straight to put everything over 2b. Ends up on the bottom here. Okay. All right, and all of that is still equal to this. So now I'm looking for suggestions.
So you could take the reciprocal of the right side.
Reciprocal of this side and put it over here, right? In other words, putting all the v's on one side, right? Exactly. So that's going to be 2v dv over 4 plus v squared. Very good. And what about the x stuff? Good. So we move the dx up to the other side. Remember, you can't put dv's or dx's on the bottom by themselves. So you have to flip them up to the top. And now what do we do? See, guys, it's separated now. It was separable, and we've now separated it. So we can just integrate this. And the integral on the left side, doable, isn't it?
Yeah.
It's not arctangent, though. Easier than that. Yeah, we can make a u substitution here, which would be what? Good, 4 plus v squared, and then the derivative of that, which is du, would just be 2v dv, which happens to be what's on top, right? So actually, on the left side, what you have is just the integral of du over u. Right? Integral of du over u, and when you anti-differentiate that, what do you get? Yeah, you get the logarithm of whatever the u was, which I'm just going to plug in here, 4 plus v squared. Okay. Do we need absolute value bars on 4 plus v squared? Wouldn't be wrong to put it there, but you don't need it because 4 plus v squared is always positive. Right? 4 plus v squared is always positive. Okay, we did that, and then what do we get on the right-hand side? Exactly, ln of x, and technically that does need an absolute value bars unless I tell you that x is positive. That doesn't matter. We'll just put absolute value bars on it and then just put plus c.
It wouldn't be wrong to just do after the value crossing everything.
No, wouldn't be wrong to do that. Okay, so we've integrated both sides. Is that the final answer? No. What else do I need to do? Okay, exponentiate both sides. Sounds good. If I exponentiate on the left, I just get 4 plus v squared. If I exponentiate on the right, can you tell me what I'm going to get? Or should we write it out? Let's write it out. It's e to the ln of the absolute value of x plus c. Right? And so I have e to that whole thing. So what can I do?
It's times e to the c.
Right? E to the c times e to the ln of the absolute value of x. We've seen problems like this before, right? And e to the c is better known as another constant, c1, right? So I'll write that as c1. And e to the ln of absolute x is better known as just x, right? I'll put absolute value bars on it though. So yeah, so we just get that. And I'm just going to steal a little bit of room right on the bottom here. And what, so what we have now is this. We've gotten it boiled down pretty good here. Are we done?
No.
Getting close though. What's wrong with this as an answer? Say again? Right, v is not the variable we started with, right, the original problem, so I have to change this back to x's and y's. So the v is actually y over x, so we're squaring that, so we'll get y squared over x squared, exactly. And that equals c1 times the absolute value of x. And I'm still trying to get this thing solved for y, because y is my unknown function. So what could I do next?
I have a question.
Yeah.
What did you get y squared?
V squared is y squared over x squared, right? What is v squared in that equation? Yeah, v is just y over x, so I'm just squaring that. So I get y squared over x squared. Good. All right, so from here, what do we